Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous lecture, we have discussed about the working and architecture of the CNN standard models like VGG19 and GoogleNet. In today's session, we will discuss about another standard CNN architecture, which is the ResNet architecture. So the contents for today's session goes like motivation for residual network, vanishing gradient problem, introduction to residual blocks and its types, ResNet architecture. In that one we will have two variants, ResNet34 and ResNet50. So we will have a quick look into the context and what was happening around the year 2012. Now in 2012, we all know that AlexNet won the ImageNet large scale visual recognition challenge, and it changed the entire picture of deep learning. And then in 2014, when GoogleNet won the challenge with VGG19 taking up the first runners of position, scientists started thinking that additional layers in neural network, if we can stack additional layers in deep neural network, it can result in improved accuracy and performance. The intuition behind adding more layers is that these layers progressively learn more complex features. So, adding more layers into the neural network will improve the performance. That was the hypothesis. Now, the question arises, can we keep increasing the layers indefinitely for better accuracy? How far we can go? To answer this question, when scientists started working on various deep learning architectures, they found that deep networks are hard to train because of the notorious vanishing gradient problem. Now, we will have a look into what exactly we mean by vanishing gradient problem. Now, we will look into what is this vanishing gradient problem. For that, let us take a graph. In the x-axis, we have the layers in the neural network, and in the y-axis, we have the gradient. And this is the curve of gradient versus layers in neural network. And suppose this is my output layer, and this is the position where my input layer is. That means, if I see, the gradient is actually reducing as it is propagating in the backward direction, and when it is coming very near to the input layer, that is at the inside of the deep neural network, we see the gradient value has decreased a lot. Okay. Now this is called as the vanishing gradient problem, and we will try to see why it happens. Vanishing gradient happens when activation functions like sigmoid and tanh squashes their values to a small range between 0 to 1, which happens for sigmoid activation function, and between -1 to +1 for tanh. So the derivatives become tiny. So we will have a look how it happens. We will take the sigmoid activation function, and we know that the sigmoid outputs the value in the range of 0 to 1. Now, if I take the derivative of sigmoid activation function, we know the derivative of sigmoid activation function when it is operating over x is sigma x into 1 minus sigma of x. So, when sigma of x is near to 0, then what happens? This term becomes very tiny, and which in turn which makes this derivative term tiny. When it is very near to 1, then this term becomes very tiny, and due to which the derivative becomes tiny. So this is what happens with the derivative of sigmoid activation function. Similarly, it happens for tanh activation function. Here the tanh activation function outputs the value in the range of -1 to +1. The derivative of tanh, if we can write, tanh activation function's derivative is 1 minus tanh of x square. Now, what happens here also? If it is between -1 and +1, this is always less than 1, and 1 minus something less than 1 is equal to is a small number. So, what happens is both for sigmoid and tanh activation function, the derivative becomes small. And during backpropagation, the gradients are multiplied through each layer of the network. So, when we are doing the backpropagation algorithm, we have seen that we use a chain rule and we keep on multiplying the gradients across the layers through the entire network. Then successive multiplication through each layer makes them very small. When a small number is multiplied by another small number, it becomes more smaller. Now, why it is a problem? We have understood what is the vanishing gradient issue, and now we will see why it is a problem. If the gradient is coming towards 0, when it is becoming tiny, then what happens is the weight updations doesn't happen effectively. So, the earlier layers stop learning as their weights hardly change because the gradients are near to 0. So, this is called as the vanishing gradient problem, and this due to this reason the earlier layers or the inside layers, they don't keep getting updated, the weights don't get updated. Okay. Now, what is the solution for this vanishing gradient problem? First is using some non-saturating activation functions like ReLU or leaky ReLU, which do not squash the input values into a narrow range, and thus helps solving the problems of vanishing gradient as done in AlexNet. So, in AlexNet we have seen that vanishing gradient problem was mitigated using ReLU or leaky ReLU function. GoogleNet used auxiliary classifiers for mitigating vanishing gradient problems. So, there are various techniques or various ways scientists have taken to mitigate the vanishing gradient problem. There is another approach which is a new approach which will be introduced in today's session. This is the residual connections. So, what are residual connections? These are shortcuts or skip connections that bypass certain layers, reducing the number of multiplications and helping to maintain the gradient size. So, we will see what exactly is the residual connection, and this was introduced by Keming, Hay and his group in 2016 in the paper titled Deep Residual Learning for Image Recognition. This group of scientists belong to Microsoft Research Group. Then we will see what is this residual block, what is the skip connections we are talking about. Skip connections connect activations of a layer to further layers by skipping some layers in between. So, what is it? We will have a look here. Suppose we have the input x. This input x goes to some layer which is having some weights. Then we have activation function ReLU. Then we have another weighted layer, neural network layer, and then it goes to something happens here. A portion of the input, or the input actually comes here, not a portion, the full one, it comes here and gets added with the output of this weight layer. So, this is called as the skip connection or identity connection, where exactly what is happening is whatever is the value that we are getting from this weight layer, that is added to x, and then we get a summed value, and then we have that summed value actually is passing through the ReLU, and then we get the output. Okay. So, this is the concept of skip connection. That means we are skipping two layers here, two layers of neural network here, and then we are adding the input from two layers behind to the output of this weighted layer, and then that summed output is going to the next activation function, which is ReLU, and then we are getting the output. Now, in normal deep network, each layer learns a mapping. Okay. So, what exactly it is? Suppose we want or in a normal network, what happens is, if x is the input, hx is the desired output. Okay. So, when we pass the input, after going through the neural network, I expect hx to be the desired output. Now, in ResNet changes, or in residual block, this changes this to a learning of a residual function. What exactly it is? It is writing hx minus x is equal to fx, or equivalently we can write h of x equal to f of x plus x. Now, where is my f of x? F of x is here, and this is my f of x plus x because my x is getting added to f of x here. and my output function actually is a ReLU activation function which is acting over f of x plus x. Okay. So, this is the concept of residual block which is used in ResNet architectures. And this is done when the input and the output dimensions are same. That means, whatever is the input that is coming to the neural network and whatever output we are getting, if both of them are having the same dimension, we use this residual block. Okay. We use this simple skip connection or the identity connection. Now, how the residual block mitigates the vanishing gradient problem, because that is what is the main reason why we are going to this residual block. So, once again I keep this picture on the right hand side of the slide and we see what is the math behind this one. Now, we all know for gradient back propagation algorithm, we take the gradient of the loss function with respect to all the layers, the weights. Now, suppose I am taking, if L is the loss function and I am taking with respect the gradient or the partial derivative of L with respect to x, that can be written as, what is x? X is here, del L by del y into del y by into del y del x. So, partial derivative of loss with respect to y into partial derivative of y with respect to x. What is y? Y is my output here, and my loss is nothing but the error between the predicted value and the actual ground truth. Now, since my y is fx plus x, okay, so or with some activation function happening that we will keep aside, just for mathematical convenience we will just take y equal to fx plus x. Therefore, del y by del x equal to, if we take the derivative of y with respect to x, we get partial derivative of f of x with respect to x plus partial derivative of x with respect to x. The second term is nothing but an identity or 1, and so we can write del L by del x equal to del L by del y, which is this term, and this term is written as I plus partial derivative of f of x with respect to x. Okay. So, what happens here is, even if this factor partial derivative of f of x with respect to x becomes small, because due to small weights or saturation of activation functions, the identity term I stops the gradient from vanishing completely. So, there is always a term which is associated with this identity term or the first term here, and that is the reason the gradient never vanishes totally. So, the gradient can flow backward unchanged through many layers. So, this is the reason why residual blocks are used and how they mitigate the vanishing gradient problem. Okay. Now, we will have a look into what are the different variants of residual blocks. There are two variants basically, the basic block and the bottleneck block. We will see what is the difference. First, we will have a look into the basic block. So, in basic block, suppose we have an input x of d dimension, and then we have two convolution layers, 3 cross 3 convolution, 2 layers of that one. Of course, in between there can be activation functions, and then this input is going and getting added here to the output of the second convolution operation, and we get the output from after the summation of the output of 2 convolution layers and the input layer, we get the output here. Whereas in bottleneck, what do we see? We have the same input d dimension, then we go through 1 cross 1 convolution, 3 cross 3 convolution, again 1 cross 1 convolution, in between we have the ReLU activations. Okay. So, what is happening here? We all know, we have seen in our previous lectures that 1 cross 1 convolution, they reduce the dimension or decrease the number of channels compressing the feature map. Okay. So, here what happens is this 1 cross 1 convolution decreases the number of channels, then in that decreased channel feature map 3 cross 3 convolution is used, again it goes back to, and then once again 1 cross 1 convolution is applied to the output of the 3 cross 3 convolution, and what does this 1 cross 1 convolution do? It restores the original number of channels. Okay. So, it is first in bottleneck block, what happens is first it reduces the number of channels, then it actually gives the convolution 3 cross 3 convolution, and then again it restores the original number of channels, and then there is an addition with the summation, not summation, the addition of the input x with the output here, and then we get the output total, the final output here. Okay. So, this is the difference between the residual basic block and bottleneck block. Now, the question is, why do you require the bottleneck block? What is the requirement? Because we are using this 1 cross 1 convolution, we know that 1 cross 1 convolutions are used to reduce the computational cost, because the same operation, when it is done with a 1 cross 1 convolution before, then it reduces the number of parameters. Okay. So, it basically reduces the computational cost. Now, we will go to the actual ResNet model. What is this ResNet architecture and what is the key idea? So, this architecture uses residual learning to mitigate the vanishing gradient problem, and it is the winner of ILSVRC 2015, the ImageNet Large Scale Visual Recognition Challenge in 2015. ResNet was the winner, and we will look into two popular ResNet architectures today. One is the ResNet34, another one is ResNet50. So, what is this ResNet34? How does it look like? So, it is a 34 layer network architecture inspired by VGG19, in which the shortcut or skip connections are added. Okay. It is a 34 layer network. We can understand very clearly because the 34 number is here in the architecture. So, we have an image 224 cross 224 cross 3, that is the size. Then it goes into a 7 cross 7 convolution of 16 filters and stride 2. Then it goes through a max pooling layer of stride 2, and max pooling layer, we know that it reduces the spatial dimensions and extracts the low level features. Then we have something like conv2 underscore x, conv3 underscore x, conv4 underscore x, conv5 underscore x. These are various blocks which we will be talking about in my next slides, and these are basically the residual blocks. So, there are 4 residual blocks, and we will explain them in the next slide. And then after conv5 underscore x, conv5 block, it goes to average pooling and of 7 cross 7 size. Then it gets flattened, we get a feature vectors. Then we have the fully connected layers of 1000 nodes. This 1000 is coming because we have 1000 classes for classification in the ImageNet dataset, and then it goes to the softmax. It goes to the softmax activation function, and we get the output. So, this is the overall ResNet34 architecture, and we will now see what is there in conv2x residual block. So, if my input size is 56 cross 56 cross 64, which is coming after the max pooling layer, after the convolution, first convolution layer and max pooling layer in my ResNet34 architecture, and this is the input size, and then it goes through 3 cross 3 convolution, 64 number of filters, another 3 cross 3 convolutions, another one. So, there are 1, 2, 3, 4, 5, 6, layers of convolution of 64 filters, and there is a skip connection between the input and after 2 convolution layers. This is the basic residual block 1. Again, between second and fourth, we have another basic residual block 2, and this is the third basic residual block 3. So, where we are using the skip connections so that the gradient does not vanish. And what happens is, so here if you see, the input dimensions are in the number of channels is 64, whereas output also is 64 channels. So, we can use the basic residual block because there we do not need to do anything to the change in the channel numbers or the dimensions remain the same. Okay. Then we will look into the conv 3x architecture, what is there. So, here also the input size is 56 cross 56 into 64. This goes through multiple number of 1, 2, 3, 4, 5, 6, 7, 8. So, there are basically 4 blocks of residual skip connections we will see. So, here from the input to this point, then again from the second to the fourth, again. Now, if we see, there are 2 types of lines that I have given. One is a dotted line, another one is the bold line. These are all the connections, skip connections. Now, what is this? What does this dotted line means? It means it is a projection shortcut. We will see what is a projection shortcut in the next slide. Right now, we will keep it as a different one from the bold one, which is an identity shortcut. Identity shortcut means directly we are adding the input x to the output of the convolution layer. Okay. So, in between 4th and 6th also it is a identity shortcut, then in between 6th and 8th also it is an identity shortcut. Now, if we see the input size, the number of channels was 64, whereas here in the output size the number of channels has become 128. Okay. This is the reason we require the projection shortcut. I will explain in the next slide. Now, this is my conv 3x structure. The output now goes to the conv 4x. What does conv 4x have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Basically, there are 12 convolution layers that, and there will be skip connections between after every 2. So, we have a skip connection between the input and after the second layer, then second and fourth, then fourth and sixth, then 6th and 8th, then 8th and 10th, and then 10th and 12th. Okay. So, this is once again the first one is a projection shortcut, then the next the others were the identity shortcut. The output from here now goes to conv 5x, where we have 1, 2, 3, 4, 5, 6 convolution layers, and there is skip connections between the input and the second one after the output from the second and fourth and 6th. So, this is how the conv 3x, 4x and 5x looks like, and after this one it goes to average pooling, and then from there flattened feature vectors, then the fully connected layers through softmax activation function. Okay. So, those things will continue here. Now, we will see the difference between the identity shortcut and the projection shortcut. What exactly is the identity shortcut? So, identity shortcut directly does a identity mapping, that is hx equal to fx plus x. So, this x is directly added to the whatever output I am getting from the convolution layer. Used when the input x and the output of the main layer block fx have the exact same dimensions. When the input and output have the same dimensions, then we can use the identity shortcut. Whereas in projection shortcut, it requires a modification of the input. So, hx equal to fx plus some projection of the input. So, what exactly is this one? Used when dimensions of the input x and the main layer output fx do not match. This happens when the input dimension and the output dimension, they do not match. In that case, input x must first pass through a linear projection, typically a 1 cross 1 convolution with a stride to resize it. So, this means there will be a 1 cross 1 convolution which will go through, through which the x will go through, and then it will be resized, and due to this operation only we will be able to do an element wise addition operation can be done after the skip connections. So, we will now have a look into the ResNet50 architecture. We have an input image 224 cross 224 into 3, it is an RGB image. Then it goes into a 7 cross 7 convolution of 64 filters, stride 2. Then we have the max pool layer, which the output of which goes to the first block, which is having 1 cross 1 convolution, 3 cross 3 convolution, again 1 cross 1 convolution. The 1 cross 1 is 64 filters, 3 cross 3 64, and 1 cross 1 convolution 256. This block is multiplied 3 times and we get this conv 2x, and then we have the second block again having 1 cross 1 convolution of 128 filters, 3 cross 3 convolutions of 128 filters, 1 cross 1 convolutions of 512 filters. This is multiplied 4 times and this is our conv 3x. Then we have the third block, the 1 cross 1 convolution of 256 filters, 3 cross 3 convolutions, 256 filters, 1 cross 1 convolution, 102 filters. So this block is multiplied 6 times and this is my conv 4x, and then the output of this one goes to the last block, which is having 1 cross 1 convolution 512 filters, 3 cross 3 convolutions of 512 filters and 1 cross 1 convolution of 2048 filters. So this is my conv 5x and it is multiplied 3 times. And if we see the structure 1 cross 1, 3 cross 3 and 1 cross 1, these are basically the structure of bottleneck blocks. So we have here 1, 2, 3, 4 bottleneck blocks, and then the output from conv 5x goes to the average pooling layer, then it goes to the fully connected layer and with the softmax activation function. Now we will see why this 50 has come into picture. How many layers are there? 50 layers here. We will just have a look. So here in the first convolution layer we have one layer. Then we have from conv 2x there are 3 layers into 3, so 9 layers are here. Here 3 convolution layers into 4, which gives me some 12 layers, and then here 3 layers of convolution and it gives into 6, so it is 18 layers, and here it is again 3 into 3 9, which is 9 layers coming from here, and the fully connected layer 1 layer. So if we add them we get 50 layers. So that is the reason it is named as ResNet50 architecture with total parameters of 25.6 million parameters. So my conv 2 layer is having 1 cross 1 convolution 64 filters, 3 cross 3 convolution 64, 1 cross 1 convolution 256. The same block is multiplied or it is repeated in conv 2_3 also, and when we see the input in conv 2.1, it is 64 channels where the output is 256. So here we need to use projection block, and in conv 2.2 and conv 2.3 there is no change in the once you have gone to 256 channels, the output also is 256, so no need of using projection block, we can use the identity blocks here. Similarly for conv 3x also I have shown there are 4 times the same block has been repeated, and here also there is a change in the channel numbers. Input was 128, output is 512. So the first block uses the projection, then the second, third and fourth uses the identity block. Similarly conv 4x is multiplied 6 times, so conv 4.1, 4.2, 4.3, 4.4, 4.5 and 4.6 exactly the same things. The first one uses the projection block and the others use the identity block. So, and this is conv 5x, 3 times it has been repeated, 5.1, 5.2, 5.3, 5 once again there is a mismatch between 1024 and 2048 the output channel numbers. So the first one uses the projection block, the second and third uses the identity block. And then this is a table which gives you there are various variants of ResNet model 18, 34, 50, 101, 152, 1202. So you can have a look into the block types that are used here and what are the depth to which it has gone. And with this one I come to the end of today's session. Let us have a quick summary of whatever we have learned today. We have started with what is the motivation for coming into residual networks, and it was nothing but the vanishing gradient, whether it was nothing but that the number of layers, increase in the number of layers in the deep neural network is expected to have much more improved performance, but it was seen that training those very deep neural network was difficult because of vanishing gradient problem. We have seen what is the meaning of vanishing gradient problem, why it is a problem, and how it can be solved. So residual networks is one of the ways in which vanishing gradient problem can be mitigated, because it uses something called as a skip connection, which adds a portion of the input and it skips 2 layers and then goes and gets added to the output of that layer. So we have seen how the skip connections, they help in mitigating the vanishing gradient problem. Then we have seen what are the residual blocks, what are the types, the basic block and the bottleneck block, what is the difference between them. Why bottleneck blocks are used? They are used to reduce the computational cost because they use the 1x1 convolution. Then we have looked into the architecture of ResNet34 and ResNet50. We have looked into how the residual blocks and the bottleneck blocks are used in both this architecture. So with this one, I come to the end of today's session. I hope you have found this session enriching, and in the next session, we will be discussing about transfer learning, and that is a technique where we use these pre-trained standard CNN models for some other task. So we will go into that one in our next session. Till that time, take care and happy learning.